Ever wondered how we know what elements lie in other planets' atmospheres? Ever wondered what those strange, disjointed rainbows were on that poster in your middle school science classroom? If so, you've come to the right place, because they both have everything to do with how atoms emit and absorb light.
Electrons orbit an atom's nucleus at very specific energy levels. Because negatively charged orbiting electrons attract positively charged protons from the nucleus, electrons need more energy to orbit further from the nucleus and resist that attraction. One way to excite electrons to higher energy levels is to direct photons, or light particles, at them. Photons also function like waves, and they move at specific wave frequencies for different colors to be seen. Photons moving with higher frequencies, meaning smaller wavelengths, carry more energy. Lower frequencies in turn correspond with lower energy levels. In this demonstration, the electron first orbits the nucleus in its ground state, its lowest energy level. When hit by a photon, shown as the ball, that moves with the exact energy amount needed to boost the electron to the next energy level, the electron absorbs it. Here, the absorbed energy corresponds with that of green light, hence the green ball. The electron is now in an excited state and orbits further from the nucleus. Eventually, it releases that exact same amount of energy to return to its ground state and emits the photon.
So how do we see how this affects visible light? Well, we look at both the emission and absorption spectra and compare them to the continuous spectrum.
That's the complete rainbow of colors formed by unfiltered white light passing through a slit and then a color-separating prism. Now let's look at an absorption spectrum. It's created when a light source, like a star, shines through a cool gas. You can view the gas as a sort of filter that only lets certain light wavelengths through. The gas is made of one or more elements, and its electrons only move between energy levels at wavelengths unique for each element's atoms. To jump to higher levels, electrons absorb photons at these distinct wavelengths, creating gap lines, called absorption lines, in the continuous spectrum. By shining the same light through different gases, we can find the lines showing where these energy level transitions occur and match them with those of known elements. This lets us identify which elements and molecules are in the gas. You can also look at an emission spectrum, the opposite of an absorption spectrum. Heated gas particles have kinetic energy, or motional energy, to convert into light. This means that its excited electrons lose energy by emitting photons at specific wavelengths, and thus distinct colors. So, if the gas is identical to the previous one, these emission lines are in the same places as the gaps in the absorption spectrum. The wavelengths emitted depend on the atoms present in the gas. Each element's atoms absorb and emit light at different wavelengths, so absorption and emission lines vary by atom or molecule.
I hope now you understand how both light emission and absorption works in atoms. Stay curious!